Okay, Matt Roscoe here at the University of Montana, and we'll begin our course with a discussion of instantaneous rates of change. Now this has to do with section 2.1 in your text, and I do want to just quickly address the fact that we aren't starting in chapter 1, and the reason we're doing that is the first chapter and its sections are largely a review of pre-calculus topics, and I will point to those chapters in case it's been a while. When we need that knowledge later in chapter 3. So if you need to do some reviewing then you can. But for now, let's start with chapter 2, which is really the first true topic in the text that has to do with calculus. And it has to do with this topic of instantaneous rates of change. It's a perfect place to start our course because calculus, broadly construed, is the mathematics of change and rates of change. So what better place to start than here? So in this video lecture, what I plan to do is give you an opening example, so give you some data and talk about how we could use the data to compute average velocities. And then we'll move on from there to talk about how we could use that data to extend our investigation to try to get a sense of, well, what instantaneous velocity would be. And then once we do those two numeric calculations, what we'll do is then move on to talk about visualizing velocity graphically and then generalizing what we've done as the derivative and how it's interpreted. So let's go ahead and get started. So one example here to get us rolling. So suppose that a pumpkin's launched and from a digital movie of the trajectory, the following data is obtained. So let's say at time 0 seconds, we're at a height of 0. And then after 1 second, we're up to 88 feet and so on. So just to give you a little bit of, I guess, inspiration for this, let's go ahead and watch a movie.
Okay, go ahead. Yeesh. Okay, go ahead.
Hit it again. Watch it one more time.
Yeesh.
I love the guy's exclamation. Yeesh. So that gives you a little bit of an idea of this data. I did actually time it. It is in the air about 6 seconds, and I'm just guessing at the height itself, but let's just suppose that those data are indeed true, and let's talk a little bit about what we might do with the data. So, how could we use the data for the pumpkin to compute average vertical velocity of the pumpkin over the following intervals? So what I mean by average vertical velocity is I mean how fast it's going in a vertical sense, up and down. And we know this pumpkin has a positive vertical velocity until it hits its apex, and then it turns around and comes back down in a vertical sense. So picture maybe instead of the pumpkin going horizontally, picture it being fired directly straight up and down. And if we scroll back here, if it was straight up and down, then we'd know that it traveled straight up in 1 second 88 feet. In the second, it was at a height of 144 feet and so on. So how could we use the data to compute that velocity over these different intervals, 0 to 2, 1 to 2, and then 2 to 3. So let's just assume that we're kind of after this idea of how fast is this pumpkin traveling when we're exactly 2 seconds after launch. So one way we might be able to think about it is, well, we could see how fast on average it is from 0 to 2, or maybe make the interval a little closer to 2 by looking at the interval from 1 to 2 seconds, or just perhaps after 2 seconds and taking a look at the interval from 2 to 3 seconds. So let's go ahead and switch over and talk a little bit about how that looks. And I'll bring up my camera here and we'll do some work together. Okay, so we have this data. I guess you can see that all right. So the data looks like this. We have time and I guess height or distance. I'll put it down as distance. I got some bad lead, sorry. Should have been prepared for this, sorry. Okay, here we go. So time and distance, time we're told 0 through 6 seconds, so 0, 1, 2, 3, 4, 5, 6 seconds, and then distance we're told, well, 0, at 1 second we're at 88 feet, at 2 seconds we're at 144 feet, at 3 seconds we're at 168 feet, at 4 seconds we're at 160 feet, at 5 seconds we're at 120 feet, and at 6 seconds we're at 48 feet, and at 7 seconds I think we're back to 0. And the question is, well, so number one, how could we compute the average velocity for the interval from 0 to 2 seconds? Well, let's just think about that. From 0 to 2 seconds, I can see that we've traveled 144 feet in 2 seconds. So that's pretty easy to do. If we wanted to know what the velocity was, we would do the change in distance over the change in time. So the change in distance is, well, I guess to belabor the point a little bit, to generalize, 144 minus 0, so it's height at the end of the interval minus the height at the start of the interval, the time at the end of the interval minus the time at the start of the interval, so 2 minus 0, we get 144 over 2, so I believe that's 72. Now let's just think in terms of units. Time is in seconds and distance was in feet, so the change in distance would be in feet and the change in seconds would be in seconds, so it's traveling over that interval an average velocity of 72 feet per second. Okay, let's try the next question. The next question asked, well, how about the interval from 1 to 2 seconds? So here we're looking at this interval from 1 to 2 seconds. To calculate the average velocity, what we would do again is take the change in the distance over that interval and divide by the change in time over that interval. So it'd be 144 minus 88 all over, let's see, 2 minus 1 seconds. So let's see, what is that? 144 minus 88. So 56 feet in 1 second. So it's just 56 feet per second. So kind of an interesting phenomenon. It's actually slower in the interval from 1 to 2 than it is in the interval from 0 to 2. And I guess you can kind of think about that as, well, this pumpkin, it is slowing down continuously as it rises due to the force of gravity. So it should actually be slower in this interval. So use that notion to get an intuition to build your intuition about the next interval. The next interval we were interested in is this interval from 2 to 3. So from 2 to 3, oh, sorry, I didn't fill that in. 2. Let's see, from 2 to 3, we could calculate the velocity as delta d over delta t. So let's see, it would be 168 minus 144 all over 3 minus 2. So let's see, 168 minus 144, that's just 24 over 1, so it's 24 feet per second over that interval. So again, it should make sense to you that it's moving slower in that interval from 2 to 3 than it was in the interval from 1 to 2 because of the effects of gravity. So I think we've got a pretty good sense of what's going on there. It seems like we can calculate these average velocities directly from the data by taking deltas, basically, a change in distance divided by a change in time for any interval we want. So I'll go ahead and minimize that, and let's talk a little bit about what we've just, how we could extend this. Now suppose that the height, the function, height as a function of time is equal to negative 16t squared plus 104t. And what it does is it provides the height of the pumpkin in our introductory examples. How could we use this, this function to find the instantaneous velocity at t equals 2 seconds? Now you might be asking, well, where did this thing come from? And let's not worry too much where it comes from, but just verify maybe in your own time that if you, for example, plugged in a t of 1, um, we would have 1 squared, so a minus 16 plus 104t, so 104 times 1, so we get 104 minus 16, which would be 88, and I believe 88 is what we were after 1 second. So this particular function can be used then to produce all the data that we have, as well as points in between. So how could we use this function now to find the instantaneous velocity at t equals 2 seconds? So negative 16t squared plus 104t. Let's go back and talk about how we can use that function. So I'll write the function down. It's h of t equals negative 16t squared plus 104t. And the question is, well, we kind of know what's going on around 2 seconds, right? We know that prior to reaching 2 seconds, it's traveling, well, these are probably more accurate because they're closer. It's 56 feet per second squared over the time interval 1 to 2 seconds, and then 24 feet per second squared over the interval from 2 to 3 seconds. So the question is what's it doing right at 2? Not in the second before 2, not in the second after time equals 2, but exactly at time equals 2. How fast are we? Now, your intuition should tell you that we're someplace in between here and here, right? And the question is where exactly. So let's see if we can get a handle on it. So one thing that should occur to you is that what we could do is we could just look at a smaller interval, something closer to 2 than 1 second away, like we did in the last example. So what if we looked at the time interval a half a second before 2? So what if we looked at, say, the time interval? I'll just put this down as the first investigation. So from 1.5 seconds to 2 seconds. That would give us a narrower average velocity interval than the previous example. And since we've got the function, we can easily find what the height is at 1.5 and what the height is at 2. Well, we know what the height is at 2. It's 144 feet. But let's go ahead and put the function into our calculator. So I went ahead and wrote it into the y equals editor. And then we can use the table. If we go to the table, we can let the table start at 1.5, and we can let the table jump by 0.5. So the table start is 1.5 and delta table is 0.5. That's in the table setup menu, which is above window. So now if I go to the table itself, it looks like at 1.5 seconds I'm at 120 feet, and at 2 seconds I'm at 144. So we can easily now calculate the velocity here as the delta d over the delta t. The change in distance is going to be, let's see, 144 at 2 seconds minus 120 at 1.5 seconds. Now the change in time is, let's see, so time is 2 minus 1.5, so second minus the 1.5 second, 1.5 seconds. So it looks like on top we'll have 24, and on bottom we'll have 0.5. 24 divided by a half, well, that's going to be 48 feet per second. So notice that 48 is indeed in between the 56 and 24. Let's go ahead and improve our estimate. So I'd ask you now to just reflect on that. How could you get even a better, more accurate representation of the velocity at time equals 2 seconds? Your intuition should immediately lead you to shortening this interval. So for example, instead of the time period 1.5 to 2 seconds, why don't we look at the time period from 1.9 to 2 seconds? So we'll carry that out. That's easily done on the calculator again. If I go to the table setup, I want it to start at 1.9, and here I want it to step by a tenth. And now I'll go to the table and take a look at what. So now we're getting into decimals. It looks like at 1.9, and I'm at 139.84 as my height. So let's go ahead and run through it again. Delta D over delta T. It's going to be 144 at 2 seconds minus a tenth of a second before. It's at 139.84. And then let's see, 2 seconds minus a tenth a second before. So let's see, it's going to be 144. I'm going to have to do this on my calculator. minus 139.84. So it looks like it's about 4.16 is the difference on top there. 0.1 is the difference in time, so 41.6. Okay, feet per second. Let's take one more. Why not? Get a little bit closer. 1.99 time is between 1.99 and 2 seconds. Let's do our v as velocity as our change in distance over change in time. So it's going to be 144 minus, let's find out what we are just 1/100th of a second before. So I'll go to the table setup. We'll start at 1.99 and we'll change by 0.01 and then go to the table. So at 1.99 I'm at 143.6. And let's see, 2 minus 1.99. So it looks like the difference here is just 4/10. So 0.4 over 0.01, which I think is going to give us 40 feet per second. And we can certainly see that these differences are getting smaller as our deltas in terms of the time intervals are getting smaller. So what we would expect is that these things would eventually converge to some particular number. I should note too that it would probably be worthwhile to do this from above as well. You notice that we're converging from below. In other words, the delta t is converging to 2 from below, or getting closer to 2 from below. We could also do this, above the interval. So we could put, for example, from 2 to 2.5, from 2 to 2.1, from 2 to 2.01 to see if we're getting a similar convergence from above. And indeed you will, and what you'll find is that we're getting really, really close to 40 feet per second, which seems to make sense in terms of these two numbers. We're roughly in the middle there, but not symmetrically in the middle, if I'm not mistaken. Oh yeah, I guess we are at the average. So anyway, 40 is right in the middle of the two velocities there. So let's just summarize and see what it is that we've really learned here. So the first thing you should have that should have occurred to you is that this data we could have easily plotted, and it turns out that when you plot it, you do get something quadratic that looks like this. So the pumpkin data can be visualized graphically this way. So what was it that we did when we computed the average velocity of the pumpkin over the time interval from 0 to 2? Well, literally what we did is we found a change in time from 0 to 2 here, and a change in height from 0 to 144 here, and we divided those two numbers. So we took 144 and we divided it by 2, and we got 72 feet per second squared. So you should immediately recognize that what we really did is we calculated the slope of the red line for the data given in our example. And of course, that slope was a little bit different when we computed the slope in between the time for the time interval from 1 to 2. Here we had a difference in time of just 1 second, so from 1 to 2, and we had a difference in height from, I think, 88 to 144 feet. So the slope was, let's see, 88. Let me look at my data here really quick. It was 56 was the change in height. So this vertical distance is 56. This horizontal distance was 1. So a slope of 56 here, whereas before we had a slope of 72 here. So a little bit flatter slope. And then even flatter slope here for when we looked at the change the average velocity computation over the interval from 2 to 3. Here the horizontal component was 1 second, but the vertical component was only 24, so quite a shrinking in that slope. So literally what we're doing when we compute the average velocity, it's the slope of the line that connects any 2 points on a distance time graph. So now let's think a little bit about what we were doing when we did instantaneous velocity. Here what we did is we first said, well, let's take a look at a point that's in between. First we were given this function, so we knew this blue graph, meaning that we can take any point on that graph. We can compute any point on that graph. So why not compute something that's a little bit closer to 2? And that's what we did. We computed this red point's height. Turned out that it was 120. And so we used this little triangle here to compute our slope and found that we got a slope of 48 feet per second. So then we moved it a little closer and said, well, what happens if we're just a tenth away? We got a slope that was a little bit flatter than 48. It was 41.6. And moving it even closer, we got something even flatter than 41.6, something close to 40. And so that's what we're doing when we're computing the instantaneous velocity. We're just taking points closer and closer to the point at which we want to know the slope of the graph, or in this case, the velocity of the pumpkin at time equals 2 seconds. So putting it into words, the instantaneous velocity is the slope of the distance time graph at a point. So it's more generally thought of as the instantaneous rate of change of distance with respect to time. So in this particular context, it's the instantaneous rate of change of distance, the y value, with respect to time, the x value. So talking a little bit more about what we've just done and kind of bringing our, I guess, first presentation to a close here, what we've been doing is leading up to this idea of the derivative. And so let's define it right now. The derivative of f at a, written f prime of a, is defined to be the instantaneous rate of change of f at x equals a. So literally the derivative is this computation that we did when we were trying to find the instantaneous rate of change of the pumpkin at time equals 2 seconds, or the instantaneous velocity at time equals 2 seconds. So we computed what we found. We computed a derivative when we found that pumpkin seems to be moving about 40 feet per second, right at 2, when we look at velocities right around the interval at 2. So there are really two interpretations of the derivative, and I will make this clear, and then we'll finish. The first interpretation is that the derivative of f at a is equal to the slope of the function at the point a comma f of a. So it's literally the slope of the function. You could also think of the derivative of f at a as equal to the slope of the tangent line to the curve of the function at a comma f of a. So you could either think of it as the slope of the function itself, or the slope of a curve, a tangent line to the curve of the function at that point. So let's just take a quick look at this and end on this. So we were discussing this whole idea of what's happening around time equals 2 seconds. So I'll go ahead and put in the tangent line at time equals 2 seconds. And so the idea is the derivative at time equals 2 seconds is one of two things. It's either the slope of this red line, or it's the slope of the blue curve at that point. Now that might not make a lot of sense to you, because you're thinking to yourself, well, how can something that's curved actually have a slope? But here's the answer. What we're going to do is we're going to zoom in on this point, and we'll just keep zooming in until we get really, really close. And as we get really, really close, you can see that the slopes of those two lines, and we should probably make the red one a little bit deeper here. Let's see if I can make it deeper so you can see it a little better. That the two lines kind of seem to be growing closer and closer to one another's value as I get closer and closer in. So what you'll notice is if I turn the blue line off, the red line that's the tangent line, and we could think of the slope of that line as being the derivative of the function at that point. Or we could turn off the red line and think of this blue line, which is indeed curved, but getting closer and closer to being straight the closer I get to, or the more I zoom in. So that's the two interpretations of the derivative at a point. It's either the slope of the tangent line, this red line, or it's the slope of the function itself, the blue line. So those are the two interpretations. And again, we think of these functions as infinitely zoom-inable, and as we get zoomed in to a very, very highly magnified setting, then these two numbers become indistinguishable. I guess these two interpretations become indistinguishable one from the other. It's either the blue function or it's the red tangent line. Both of those are interpretations. Okay, well, that concludes our lecture for today and or for this chapter, and I wish you luck on your homework and let me know if you do have questions.